All right, so let's go ahead and get started. So as promised, I have a Van de Graaff generator here. And we remember from Thursday, we were talking about how the Van de Graaff generator works. And so basically, you see on the inside of here, it's nice because it's clear, you can see the belt. There's this belt that is rubbing up against a brush at the bottom. And what this is doing is it's ripping electrons off of the bottom and it's depositing them all on the top. And so what we'd like to do is we'd like to predict what's going to happen when I put these pipe plates up here. So go ahead and talk about that. We did talk about it briefly on Thursday, but try to remind yourselves what you think is going to happen when I'm depositing all this charge on the top. Okay. So we'll spend a couple of minutes talking about that. Just fill up my water bottle. So what do you guys think? What's going to happen? Going to lift off? Okay, good. Okay, so like I said, we did talk about this on Thursday, so we should know that what's going to happen with these is they should repel each other because you're depositing all this charge on the top sphere here, and then that charge is going to try to spread out as much as it can, and that means some of it's going to go into the plates. And as that happens, the plates are each going to become negatively charged, they're going to repel each other. So let's see this in action. I have to turn this up. Nope. Might take some time. It's actually a little bit anticlimactic because the permeability of the permittivity of free space changes based on the temperature, but I've seen this before where it's happened. And let's discharge this so I don't electrocute myself. I've seen this before where they've really come up quite a bit more than that. So let's try something similar. And now I have a bunch of packing peanuts in this plastic container. So what do you guys think is going to happen here? So go ahead and talk to each other and see what's going to happen with this one. All right, so what do you guys think? What do we think was going to happen with this one? Any predictions? Yeah.
Would they pop up out of the...
They might. Why?
Because the negative charge will move through the container, the peanuts, and since they're neutral right now, when the charge comes in.
Right. That's a good hypothesis. Anybody else have any ideas? Okay, so let's see what happens here. I'm going to do this one. So it's exactly right. So the thing is, and again, it's not the best day for it. I've seen this happen before where they all just shoot out immediately. But we're getting there a little bit. So the thing you want to take in consideration here is that this is in contact with this, and it's not a perfect insulator, right? These might be insulators, but charge can still flow a little bit through them. And so because this is in contact, it's the same exact thing is going to happen as the pie plates. Okay, now if this was a perfect insulator, then none of the charge would be able to come across and flow through the plastic we have here. Okay, so that's that. Okay, so let's get into our work for today. So we're starting off kind of where we left off last time, and this was doing calculations with Coulomb's law. So take maybe about 10 or 15 minutes to work on this one, and then we'll talk about it. Okay, so let's go ahead and talk about this one. So the first thing that we want to do with any problem like this that's just given verbally, so you don't have a picture, is to make your own picture. And so what the problem says is you have a square that has sides of 0.25 meters, and every corner of the square you put an electron. So let's go ahead and draw that. And so have something that looks like this. This is a distance of 0.25. This is a distance of 0.25. And let's give these charges names, or give them labels. So I'm going to call this 1, 2, 3, and 4. Okay? So we want to find what the force is on charge 2. And so in order to do that, we want to find the total force, F total, acting on 2, which means I want the sum of the forces acting on this. So I have some force that acts from 1 to 2. That's going to point this way, so this is F12. We have some force that acts from 3 to 2. That's going to point like this, so this is F32. And then the final force is going to point from 4 to 2. And so this goes like this. So this is F42. Okay? So the total force is going to be equal to the sum of these forces. So this is F vector 1, 2 plus F vector 3, 2 plus F vector 4, 2. Okay? Now we just need to calculate what these are individually. And so F vector 1, 2 as a magnitude is going to be equal to K Q1 Q2 over R squared, where this is going to be equal to 9 times 10 to the 9 newtons per Coulomb, times 1.6 times 10 to the negative 19 coulombs squared, divided by, this should be coulombs squared. This is coulombs squared. Divided by the distance from 1 to 2, which is just the 0.25 meters. Okay, so this is 0.25 meters squared. Okay, so when we do that calculation, we would get some number. That actually happens to be the same number that we would get when we do the calculation for the force that 4 acts on 2. Why is that the case? Why am I going to get the same force acting from this one to this one as I get from this one to this one? Yeah?
The length is the same.
Right. That's one part of it. That's one part of it. So the distance is the same. There's one other reason why. Yeah?
About 45-degree angle.
That comes up later here. Yeah? The charge is the same. So because the distance is the same and the charge is the same, we're going to get the same force for this. So actually we can say the magnitude of F12 is going to be equal to the magnitude of F42. Okay? Now, the last one we need to calculate is what the magnitude of F32 is. So F32 is going to follow very similar. So this is going to be K Q3 Q2 over R squared. And so this is going to be equal to 9 times 10 to the 9 Newton per Coulomb squared times 1.6 times 10 to the negative 19 coulombs squared. Now, what's going to be different here is this distance. So this distance is different. But we know that this distance is going to be 0.25 meters. And so we're forming a triangle here. And so in order to find this distance squared, this is just going to be 0.25 squared plus 0.25 squared square root. But I want R squared, not R, and so this is just going to be 0.25 squared plus 0.25 squared. Okay? And this is going to give us another number. Now, in order to find what the total force is here, what we need to do is we need to plug in, or we need to evaluate this in terms of vectors. So we can say that F vector 1, 2 is going to point in the x direction, and so this is just the magnitude F12 in x, right? Because this is pointing to the right, and I've been using i's here, so this is going to be an I hat. This points this way. It doesn't have anything in j, plus 0 in j, okay? F vector 2, 3, F vector 4, 2 only points in the y direction. So F vector 4, 2 is only going to point in the y direction, so it has nothing in the x direction. And plus mag F42 in the j direction. Okay? F32 has components in both x and y, right? Because this is pointing at some angle, so it's got a little bit in x, a little bit in y. So these are the coordinate systems I'm using here. So this is x, this is y. But we know that this is a 45-degree angle. because this is a square. And so what that says is the component in x is going to be the hypotenuse of this triangle times the cosine of 45, and the component in y is going to be the hypotenuse of the triangle times the sine of 45. And so what that says is that this is going to be mag f 32 times cosine of 45 degrees I hat plus mag f 32 times the sine of 45 times j hat. And then what we want is we want the total force, so we just add these together, right? That's where we started here. We said that the total force is just the sum of the vector forces. And we've found each one of these vector forces and components. So the last thing we need to do is to add these together, and we would have calculated what they were explicitly already. And so what that says is that this is going to be F vector total, which is going to be equal to about 5 times 10 to the negative 27 newtons in the I direction, plus 5 times 10 to the negative 27 newtons in the j direction. Okay? Looks good? Any questions about this? So any type of problem I could ask you for this, you know, I could change the geometry a little bit. I could, instead of giving you a perfect square, I could give you a rectangle, or I could give you a triangle, or if I was mean, I can give you a pentagon, right? But the process is always the same. What we need to do is we need to figure out what each of the forces are in components, and then we just need to add them together. Okay? Good, good. So let's move on to, well, actually, there's a little bit more to this one. So then the question is, what does this change if you replace all the electrons with protons? So what if these were all positive charges? Any thoughts? It's the same, right? Because it's all repulsive, right? How about if I replace the bottom left with a proton, but I leave the rest of the electrons? What's going to change there? The direction of what?
We're going to attract towards the
Right, right. So this force that I drew here, F vector 32, is going to point the other way, right? What does that change in my calculation? It's going to change some sign. I'm going to subtract them. Right, because if this F vector 32 changes direction here, so it points like that, then that means that the x component of this is negative, so I get a negative sign. The x component of this one is also negative, or sorry, the y component is also negative because it's pointing down like this. This is the coordinate system I have. To the right is positive, this points to the left, and up is positive, this points down. So the x component and the y component are going to be negative. And then of course you get different numbers here. Okay? Okay. So let's go ahead and move on to the next one. This one looks suspiciously like the same one that we just did, and there's a reason for that. I'm trying to build up to thinking about these a little bit more abstractly, not just in terms of the numbers. Okay? So I think you guys are seeing that, you know, this is basically the same question. I've just reframed it a little bit, changed the numbers, and I've changed the direction of the, or sorry, the distance. I've changed the distance between them, and I've changed what the charge is. Okay, I'm actually still on. So the question is then, do we have to do the whole calculation again? The answer is no, because we can see what's changing from one to the other. And what I'm trying to build up to is actually to do this even more abstractly and do it without numbers at all. So if we see that the distance is just changing by a factor of 2, what that means is when we look at the distances here, I'm going to get a factor of 2 everywhere, right? So this would be a factor of 2 here. This would be a factor of 2 here. And so what does that change? Well, if I increase the distance by a factor of 2, so F vector 1, 2, and I change the distance by a factor of 2. So this is just going to be K Q squared divided by R, because these charges are the same in this case, R squared. So if I make this a factor of 2 larger, that means that the force is going to decrease by a factor factor of 4, because I can plug in 2r here, and so if I plug in 2r here, this ends up being kq squared over 2r squared, which is going to be kq squared over 4r squared, right? And so all of the forces that we get end up being changed by a factor of 1/4. And so what that means is we could actually just take the components of our final answer here, and then we can divide all of these by 4. And so when we do that, this ends up becoming 1.2 times 10 to the negative 27, and this ends up being plus 1.2 times 10 to the negative 27. Okay, so this is, we're seeing some connections in the way that these calculations are related, but we want to go even more abstract. We can do this entire problem without numbers at all. Okay, so now I'm just telling you that each of these, we still have a square, but the distance between the points is some arbitrary distance. I'm just calling it some distance A. And now I'm also saying that the charges aren't identical. Each charge has some known charge, but we're going to label them Q1, Q2, Q3, Q4. And then what we want to do is we want to see what the force is in those terms. And then at the end, if I gave you some numbers and I said, okay, well, this is 1 meter, this is 10 meters, this is 0.025 meters, right? Then you could plug the numbers in at the end, but it's actually better to do all of these things algebraically, because if you understand the relationships between the variables and how you can set this up in general, it actually doesn't matter what the numbers are. You can plug the numbers in at the end. Okay, so spend a little bit of time working on this purely algebraically, and then we'll move on from there. Okay, so let's go ahead and talk about this one now. So what we're doing here is we're trying to abstract the way that we're solving these problems piece by piece, because ultimately treating these things purely algebraically ends up being a lot easier in the end, and it saves you some steps along the way, because you notice that when I solved this the first 2 times, or the way that I laid it out here, you had this intermediate step where you plugged in numbers, and then you had to plug numbers in over here. Doing this algebraically tells you what the relationship between these quantities are in a way that makes it so that you don't actually have to plug in numbers at all, or if you want to, you can do it at the end. And so let's see how this one's going to work out. So I said that there's some arbitrary charge, some unknown charge at each one of the corners here. So I'm going to give them labels so that top left is Q1, top right is Q2, bottom left is Q3, bottom right is Q4. And these have some arbitrary distance A associated with them. So this could be any distance. It could be 0.5 meters, it could be 0.25 meters, whatever distance you want. But the important thing here is that we can still set up what the force is going to be acting on this, because we know the relationship between the force and the distance and the charge. And so that's to say that the force that 1 acts on 2 is going to be equal to K Q1 Q2 divided by the distance squared, which is going to be the distance A squared. F32 is going to be equal to, double equal sign, is going to be equal to KQ3 Q2 divided by this distance squared. This distance here is going to be the square root of A squared plus A squared. So this is going to be square root of A squared plus A squared squared is just going to be A squared plus A squared. Okay. And now we can do F42. Again, this looks very similar to this, but the charge is different now, because I don't have identical charges everywhere. In principle, Q4 can be different than Q1. And so this says that this is going to be K Q4 Q2 over A squared. Okay? So now we have all of our forces in magnitudes. We just need to evaluate what the force actually is. And so it's going to be a little bit tricky, because I left this completely arbitrary, so I didn't tell you whether these charges were positive or negative. But let's assume that they all have the same sign for the time being. Okay. So if these all have the same sign, then I can say, and we'll make this a positive sign even. Actually, it doesn't matter as long as they're the same sign. So if these all have the same sign, the force that 1 axon 2 as a vector is going to be equal to this k q1 q2 over a squared times I hat plus 0 j hat, or we could have just left this as the magnitude here. F32, again, needs to be broken into components, and so this has some components like this. So this is some angle which is going to be equal to 45 degrees. This has a common factor here, so this is going to be k is equal to, actually let's write it out explicitly. So this is going to be k q3 q4 over a squared plus a squared cosine of theta I hat, and I'm leaving it even more arbitrary. In general, this doesn't have to be this distance. This doesn't have to be an angle of 45. I can plug that in later. Plus k q3, sorry, this should be a q2. q2, q4, k q2, q4 over a squared plus a squared j hat. And actually, something really interesting just happened there, and you might not have caught it. I realized I made a mistake because of the way that I'm labeling things, right? So I was looking at this and I saw, okay, well, I wrote a Q3 here, but this, sorry, it's still wrong. It's still wrong. This is 2, 3, this is 2, 3, right? So keeping track of things like this and writing it algebraically like this, I can look at this and I can say, okay, well, I need a 3, 2. I better have a 3, 2 here. I better have a 3, 2 here. But if you're plugging numbers in, you might not have that set up that way. So it's another interesting check that you can have when you're looking at these things and making sure that they're working out the right way. The other thing is I need a sign here. I got a little sidetrack, so this is going to be sine of theta, j hat. Okay. All right. Last one is going to be F42. So this is going to be F vector 42 is going to be equal to, this is going to be 0 I hat plus k q4 q2 over a squared times j hat. Okay? And then if we wanted to find the force, all we need to do is add these together, and we could, if we wanted to, write that last line. There are even some steps that I showed here that you might not even need to write, because you know that this is just the magnitude of F12, this is the magnitude of F32, this is the magnitude of F42. You didn't need to explicitly write that out, but I think it demonstrates the point nicely that you can write all of these things purely algebraically without plugging the numbers in. And then if you wanted to at the end, plug in the numbers, but try to think about these things in terms of the relationships between the quantities, and not just the fact that the charge has this number, the distance has this number. It's a more powerful way to look at it. Okay. Other questions about this? Or any questions? Yeah?
Here, I hat and j hat just means x and y.
Exactly. So this is the amount that's pointing in the x. This is the amount that's pointing in the y. And you can see that explicitly here, because if I look at my force 1, 2, what's the direction force 1, 2 points? Well, it points to the right. So it's all in the x direction. It's all in the x direction. Nothing in the y direction, right? This points like this. Look at F42. F42 doesn't have anything in the x, right? This force just points directly up. So 0 in the x direction. Everything's in the y direction. And then F32 is a little bit of both, and it actually happens to be exactly the same in both, right? Because this this is the magnitude of the vector, but it has some amount in the x direction because this is at some angle. So a little bit in the x, a little bit in the y. And if this angle is 45 degrees, then this actually ends up being exactly the same. When we explicitly did the calculation before, we saw that they were the same. And that's really because cosine of 45 is equal to sine of 45. Right? Okay, good. I hope that clears some things up if you're not familiar with the notation. Okay. Any other questions? Okay. So let's move on to the next one, and I promise this is a completely different question. So this is getting into the concept of what's called an electric field. So to this point, what we've done is we've talked purely in terms of forces. What's the force that this charge acts on a charge that's near it? But what happens to be even more powerful is to think about what field is produced by a charge. Because what you can do is you can imagine that if I have some charge that's at some point. We could think about what the force would be as if there was another charge close to it. So let's say there's a plus charge here. So I put we say put a test charge. It's usually like a really little charge. So this is a little charge here. What's the direction of the force that acts on this? It's going to point to the right. Well, what happens if I put this up here? It's going to go diagonal. If I put it up here, it's going to go this way. If I put it over here, it goes this way. And then what you can do is you can imagine, well, I don't really need this test charge here at all to know what the direction the force would point as if there was a charge there. And that's what we mean when we talk about the electric field. It's what's the direction the force would look like if there was a charge there. And then we say, well, we don't actually need to put the charge there. And then we can draw some lines to tell us what the direction these things point. Now, the important thing to take away from this is that the force is related to the electric field, and that's to say that the force acting on some charged particle is going to be equal to the charge times the electric field that it's in the presence of. Now we can walk this back a little bit more and then ask ourselves, what should the electric field be? Well, from a point charge anyway. So what's the electric field from a point charge? Well, we know what the force is on a point charge. Force on a point charge is going to be K Q1 Q2 over R squared time, and we'll treat this as a magnitude. So as a magnitude, this is K Q1 Q2 over R squared. So what do we think that the electric field from a point charge is going to look like if that's the form that the force takes when it's a point charge? So how would we solve this equation for the electric field? How would we solve this equation for the electric field? It's just simple algebra, right? We just divide both sides with a charge. What happens when I divide this equation by a charge? One of the charges goes away, right? So this says that the electric field from a point charge is just KQ over R squared, okay? And that's conceptually what it is that I'm doing here when I'm thinking about what does the electric field mean, right? Because what it means is I'm taking a charge away, and when I take a charge away, dimensionally, I have one less charge, okay? So now we understand this relationship between the force and the electric field, and the rest of the class really today is going to be exploring what the electric field is and what it means. But now that we understand this relationship, go ahead and do this calculation to find so it says a charge of Q0 is equal to 3 times 10 to the negative 8. It's placed at a particular location, experiences an electrostatic force of 6 times 10 to the negative 4 newtons. Suppose that the charge instead was replaced with a charge of 6 times 10 to the negative 8 coulombs. What would be the net electrostatic force on this charge? And then what would the force be if the charge was 7.3 times 10 to the negative 9 coulombs? Okay. So go ahead and spend a couple of minutes working on this one. So let's go ahead and talk about this one. So what we're given in this question is there's some charge in free space and it has some force acting on it. And then what we say is we take that charge, we replace it with a different charge, and we want to find what the force is on the new charge. So we can kind of draw a picture of what's happening here to say that we had some Q1 here initially, and this had some force acting on it, F1. Now, in order for this charge to have some force on it, there has to be some electric field in this region. And so it doesn't really matter what the electric field looks like. It could be spherical, it could just be pointing horizontally, but I'm just going to say that it's going to point horizontally like this. So there's some electric field in this region that's causing the force on this charge Q1. And then what we want to do is we say, okay, well, I'm going to take this charge out. I'm going to replace it with another charge. Call this some charge Q2, and this has a different force. This has some force F2. And then the third part, we replace it with an even different charge, so some Q3. Replace this with that, and this has a third force acting on it. And so what we want to do is we want to relate the charge that we have to the force and the electric field that we have here. And so what we can do is we can take the ratio of the force to the charge in order to find the electric field, right? That's what this equation here says. if I have the force and the charge, I just divide the force by the charge to find the electric field. So E is going to be equal to F1 over Q1. And if we wanted to solve for this, it's an intermediate step that we don't necessarily have to do. But this ends up giving us a value of, I believe, 20,000 here. So this is going to be 20,000 newtons per Coulomb, okay? But this E is actually the same for all of these. So what this says is that this ratio F1 divided by Q1 is actually equal to the ratio of F2 over Q2, which is equal to the ratio of F3 over Q3, which is this value of 20,000. And so if we want to find what F2 is, we could just rearrange this. So this says that F2 is going to be F1 Q2 divided by Q1. If we want to find F3, this is going to be, which is the same thing. You could do this a little bit differently, but this is E times Q2. This is F3 is going to be F1 Q3 over Q1, which is the same thing as E times Q3. Okay. So you see, again, there's a lot of power in the algebra here because you're talking about the relationships between these things before we even plug any numbers in. So when I plug numbers into this, I end up seeing that this one is going to be 0.0012 newtons, and this one is 0.00014 newtons. Okay? I believe that's what I had here. Yeah. Any questions about this? Yeah.
I'm sorry, I'm still kind of confused why you know that the same like the same field is acting on all of those. Is it just assumed?
Yeah, it's something kind of by definition for how the electric field behaves. The electric field it can be produced by a charge, right? But that electric field is not influenced by what charge is in it over here, per se, if I'm trying to find what the force is. I mean, it is in a more complicated way, but for our purposes, when we're talking about what is the electric field in this region, it's not influenced by this charge right here. It's just going to be present. You say that there is some electric field in this region. So for instance, how do you establish an electric field? You could have a pair of parallel plates that have charge on them. And if I put a charge in between those, the electric field is just produced by the two plates. I don't worry about what the electric field is produced by the individual charge.
So it's constant for your system?
Yeah.
Okay.
Yeah. Okay. Other questions? Okay. So I actually have a video based on this, so we're going to watch this, but if I remembered, I would have posted it ahead of time. But this kind of gets to conceptually, what does the electric field mean? Next class. So based off the things that I was talking about in the video, we want to see what the electric field lines look like for a positive charge and for a negative charge. So recall what I was just saying and talk to your neighbors to draw what the electric field lines look like for our positive charge and for our negative charge. So let's go ahead and talk about this one. So really straightforward, and I had just done it in the video here, but we want to talk about why the electric field lines point the way they do for the definitions that we have. So remind you that this is what's called, it's the first portion of what's called the Lorentz force law. And the second portion incorporates the magnetic field, but we'll see that later in the semester. We also know from Coulomb's law that the force between two charged particles is going to be equal to K, Q1, Q2 over R squared as a magnitude. Okay, so we could draw this to start out with because I just shown it, right? That some positive charge has electric field radiating away from it, like this, and some isolated negative charge, because the electric field would bend a little bit because of the presence of both charges. So we're going to say that these are not interacting with each other, would look like this. So in terms of these two equations that I have here, can we think about why we're saying that positive charges have electric field lines pointing away, and negative charges have electric field lines that point towards them. Why is it the case that, that this is like this and this is like this? It's all interconnected. So think about it like this. If I had a positive test charge, and I put a positive test charge here, what's the direction this is going to go? It's going to go away, right? Because this positive charge is going to repel this one. And so the force that this would act would make a positive charge move away from it. What if I put a positive charge here? It's going to suck it in, right? So this is going to pull it in this way. And so that's why when we're drawing our electric field lines for positive charges and negative charges, they have the directions that they do. Okay? Okay. So next question. So we have here a picture. We have some positive charge and some distance d. We want to figure out an expression for the electric field vector at a distance d from the positive charge q as shown below. How would this expression change if this was a negative charge? Okay. So think about the equations that we have. So the equation that we have for point charge is going to be E is equal to K Q over R squared. But we also want to make sure that when we're writing